Hi there, this is Astrophysics, Cosmology Lesson 1. This is on the Doppler shift. So the Doppler effect. So let's imagine an ambulance is travelling from left to right. And obviously its sirens going. So it's at point A it gave off a sound wave, at point B gives off another sound wave. Point C, same thing, so on and so forth. As you can see, if you're on the right hand side and the ambulance is coming towards you, the wavelength is shorter. That's the distance between the peaks. So the peaks being the red, the blue, the green, and the pink lines. So the wavelengths getting squashed together. So shorter wavelength, but the frequency is increasing as well. So that sound would be more high pitched as it's coming towards you. If it was driving away from you, then the sound would be a lower pitch or lower frequency. So as the ambulance travels forward, the sound wave in front is compressed, which decreases its wavelength whilst increasing its frequency. The speed of the sound remains the same. So the sound wave behind is stretched out, which would increase its wavelength while decreasing its frequency. All right, let's move on. So the Doppler effect also occurs with light and radio waves. So with light waves in front of the moving object, so it's coming towards you, the same effect as with the ambulance. So you get a decreasing wavelength and an increasing frequency. So the light will be bluer. That's known as blue shift. So shifting towards the blue end of the spectrum. If you're behind the moving object or it's moving away from you, the wavelength will get stretched out and the frequency will be decreased. So that makes the light redder, which is known as red shift, or shifting towards the red side of the spectrum. So essentially, if something's coming towards you, it'll blue shift. If something's going away from you, it'll red shift. So towards is blue, away is red. Right, so we've got some Doppler effect equations. So when the radial speed, that's just the speed it moves away or towards, is much less than the speed of light. For objects, close to the speed of light, you have to take into account relativistic mechanics, which is beyond the specification of the A level, obviously. So, first one, change in frequency divided by source frequency. So the source frequency is what it should actually be, if it wasn't moving, is equal to object speed divided by speed of light, or delta F divided by source frequency equals V over C. So that's the first one. Another one, change in wavelength over source wavelength being what it should be if it wasn't moving away or towards the object. And then speed divided by speed of light. And they're all equal to the Doppler shift, Z. So Z is equal to change in wavelength of frequency, which is also equal to the change in wavelength of a wavelength, which is also equal to V over C. And I know mathematicians don't like equations or expressions being written in that manner, but oh well. And please remember, V must be much, much less than the speed of light. Right, and then I've just got 3 questions for us to do. So I'm going to put them on. You have to use the equations. The equations are all on the data sheet. So let's move on. So if you're going to pause and have a go at this one, and then we'll go through it. So light of source frequency. So we've got 4 times 10 to the power 14 hertz is emitted from a galaxy that's moving away from us at 600 kilometers per second. So we're going to calculate the frequency shift and then the observed frequency. So change in frequency, which is the shift, divided by the source frequency is equal to V divided by C. So the frequency shift is going to be V over C multiplied by the source frequency. So the speed is 600 kilometers per second, so 600 times 10 to the power 3 meters per second, divided by speed of light, 3 times 10 to the 8, multiplied by source frequency, 4 times 10 to the power 14. So the frequency shift is equal to 8 times 10 to the power 11 hertz, which is a big number, but obviously as a percentage of the source frequency, it's not a big change at all. So this galaxy is moving away from us. So you need to think what happens if something's moving away. So the wavelengths get longer, and consequently the frequencies get lower, and that's just using C equals F lambda. So if it's moving away from us, wavelengths get longer, it redshifts, so frequency must come down. So what we need to do is original frequency, 4 times 10 to the, original frequency, 4 times 10 to the 14, and then subtract 8 times 10 to the 11. So that gives an observed frequency of 3.992 times 10 to the power of 14 hertz. Hopefully that went okay. Right, let's try another example. Alright, so here's question 2, if you want to have a go at this one. So in this one, we've got the Andromeda Galaxy. The Andromeda Galaxy is famously moving towards us. It's got a Doppler shift of 0.0005. The observed wavelengths are smaller. That's because it's blue shifting. It's coming towards us. So if the wavelengths are getting smaller, the frequency is getting higher. So first of all, we need to calculate the velocity of the Andromeda Galaxy relative to Earth. So let's do that now. So we've got the Doppler shift. So Doppler shift is equal to V over C. So really straightforward, this one. So radial velocity is going to be Z, Doppler shift times speed of light. So we've got 0.0005 multiplied by 3 times 10 to the power of 8, which is 1.5 times 10 to the power of 5 meters per second, or 150 kilometers per second. Right, part B, what will the observed wavelength of red light be if the source was 700 nanometers? So what we need is the shifting wavelength. So we can just use Z, because we've got the Doppler shift, is equal to change in wavelength divided by the source wavelength. So I'll rearrange to get the change in wavelength. So change in wavelength is Z times lambda. So we've just got 0.0005 multiplied by 700 times 10 to the minus 9. Or you could keep it in nanometers, it's completely up to you. So it was 0.0005 times 700. So anyway, the answer would be a shift of 0.35 nanometers, or 0.35 times 10 to the power of 9 meters. And because it's blue shifting moving towards us, the wavelength is going to get squashed. So the observed wavelength will be the 700 nanometers that we had originally, and then subtract the shift 0.35 nanometers. So the observed wavelength 699.65 nanometers. Hopefully that one went okay. All right, I've got one more example for us to do. Right, so question 3, if you want to have a look at this one. So I've got a hydrogen radio source, emits waves with a frequency 1420 megahertz. A radio telescope observes these waves to a frequency of 1430 megahertz. So the frequency is shifted up, so frequency is increased, so that means wavelength comes down. Squash wavelength, so this is blue shift, this is coming towards the Earth. So for this one, we can use the change in frequency divided by source frequency equals V over C. So the change in frequency, 10 megahertz. I'll leave it all in megahertz. Divided by the source frequency, which is 1420 megahertz. And that's equal to V over C. So I just need to do the ratio, 10 divided by 1420, 10 divided by 1420, times speed of light, 3 times 10 to the 8. So if you put that in your calculator, that'll give you 2.11 times 10 to the power of 6 meters per second. Or 2,112 kilometers per second. All right, let's move on to a summary. So if you're interested, the main thing is that if the source is moving towards you, it's blue shifting. And if the source is moving away from an observer or from the Earth, it's redshift. Hope you found that useful. Thanks for watching.